My name is Danny Chen. I'm on the Trading Solutions SRE team at Bloomberg, and I'm going to be talking about loggers and the irony around the fact that loggers give us so much information about the runtime behavior of our systems, but most logging implementations don't provide very much insight into their own runtime behavior. And this talk, even though it's loggers, is really about visibility. To get us in the right mood, I've done this kind of scrape of my captain's log, right, for relevant events. I started my career way back in 1980 at Bell Labs as a Unix performance engineer. In the mid-'80s, I co-developed what I believe to be the first general-purpose Unix kernel tracing package. I called it Casper. In '88, I spoke at USENIX, presented Casper at USENIX in '88. And in '90, I spoke at USENIX on some virtual memory performance improvements I made to SPR4, leveraging Casper and the insights that into copy on write behavior that Casper gave us. I joined Bloomberg in 2015 in the developer experience group, and recently moved over to the Trading Solutions SRE team. In between leaving Bell Labs in 1992 and joining Bloomberg, I've done a lot of different things, but they've all involved kind of handling logs and even building out log replication and log scraping infrastructure. Oh, and I'm also, I'm not teaching this semester, but I'm also an adjunct instructor at the Borough of Manhattan Community College. Okay, so outline of what I want to cover, some inspirations for this talk. It's been a long time, almost 30 years since I spoke at USENIX, right? So something had to make me want to do this. I didn't want to. Some example logging patterns and data. And one key takeaway is that I don't want to just make it like I'm focusing on logging. It's really about visibility. And I want to go into why we're in this state, I think, and how we might work our way out of it. And also, I'll close by looping back to logging and seeing what better visibility can potentially buy us. So, I attended SREcon last year in Santa Clara, right? And there were two talks that kind of resonated with me. And I wanted to take those ideas from those talks and kind of present them in the context of visibility. So, in History of Firescapes, Tanya Riley kind of gave a really nice history of New York City fire codes and the disasters that prompted their creation and evolution. So if you haven't seen the talk, I would go to the videos and watch it. It's a really nice talk. But what she did was she took the success of fire codes in preventing disasters and saving lives and said, why don't we establish some software fire codes, right? Some basic principles that we need to build scalable, reliable systems. And when she said that, in my head, I said, oh, visibility primitives. That to me would be a fire code, right? Because I've long felt that our systems are lacking some key visibility primitives to encourage writers of library and low-level code to add metrics into their own code. And I'll talk about that more a little later. And then the other talk was Antics, Drift, and Chaos. Lauren Hochstein kind of presented this idea that deviations from expected behavior are an unavoidable consequence of having complex systems that run over time. And these deviations he called antics and drift. I think the drift is kind of long-term and the antics are kind of short-term deviations, but they're deviations. He put forth applying chaos engineering to ferret these things out. But for me, an important consequence of this inevitability of antics and drift is that we need to have visibility into all levels of our stack, right? Because an antic at one level might be preceded by a drift at a lower level, right? Or drift at a higher level may be a sequence of antics from lower levels. So if we had visibility into it, we might gain some more insight. In the antics talk, he also provided an example, a case of an antic involving logging, right? Where in production, the logging volume was accidentally kind of increased, which led to contention at a logging related log, which eventually led to delays and then an outage, right? Which brought me, flashback to my own kind of logger moment. I don't know how many people have had, logger moments, but I've had my own logger moment. And this one was way back over 10 years ago, but during the financial crisis. I was a member of a middleware team at a large investment bank. And we owned the messaging and distributed transaction management infrastructure that kind of provided the glue for the distributed processing that went on in the company. So what apps would do was they would take messages off, or produce messages off a messaging bus, and update a database. And the distributed transaction management would kind of tie the two together and keep them in sync. During the financial crisis, there were a lot of volume spikes, and much larger volumes than used to. And these apps had a hard time keeping up. And so the app teams and the DBAs and our messaging team would kind of form a virtual team to kind of triage and identify bottlenecks and try to get through the crisis. The crisis, not the financial crisis, the crisis of volume, right, that we were experiencing. In one case, this app team reported 100% CPU utilization. They couldn't get enough work done because the CPU was saturated. And so I said, well, that's a user application problem. You should be profiling and looking for hotspots. And the app team very politely came back to me and said, well, yeah, we did, and it's in your logger. Right? So we were responsible for a logger, C++ logger. So it was one of those deviations from expectation, right? So I said, what, really? And I looked into it, and it in fact was in our logger. Not only was it in our logger, but it was in the string ftime function. So string ftime, if you don't know it, it's the C library function that's responsible for taking a binary kind of encoded timestamp and converting it into human readable form. And that's what loggers use to present timestamps, right? And this turns out that on Solaris 8, on Spark hardware at the time, string ftime took about a millisecond per invocation. That's an obscene amount of time even back then, right? But the more important point was that we as owners of the library had no idea. Right? We were just running the library, and people were using the library and incurring this cost without any visibility. Right? So since that time, I've been particularly sensitive with respect to logging and latencies. So when someone tells me, oh, I've got this fancy new logger that logs over the network, or I'm logging to a database, or I'm doing async logging even, right? My first question is, well, do you measure latencies? And almost always the answer is no. But what they will say is that what we can do is we can look at the utilization of the backend, right? So if the backend's busy, then obviously the clients are busy and things. And that's fair enough, right? But the thing about utilization is that it's kind of a macro measure. It's measured over seconds or minutes and things. And so what you're doing is you're relating the average utilization over that time with average latency over that time, right? That's really the relationship, right? So, and if you're interested in antics and drift, you're really looking for the deviations, right? So you need kind of some idea of the distributions. And also, SLOs and SLAs are kind of often phrased in terms of distributions, not in terms of averages, right? There's actually a talk on Wednesday, I think, titled Latency SLOs that I think is relevant, and I'm intrigued. So now with that, I'm ready to kind of present some data, right? But this is kind of just sample data and sample logging patterns. My purpose here is not for you to go back and make decisions off the numbers that you see. In fact, hopefully you can't see the numbers, right? But it's to kind of prompt you to go back and do your own measurements if you haven't done it already. Because again, it can be surprising. So here, in this example one, I'm doing standard file logging. It's in Java using the logback logging package. And all I'm doing is in a loop. It's very simple. In a loop, writing a log once a second and timing how long it takes throughout the day. It's on a production system, but the production system wasn't particularly busy, so it's kind of relatively sunny day, once a second. And I'm collecting, essentially, and displaying the histogram of elapsed times for the logs, right? And you see the histogram chart on the left is essentially a zoom in. It's for the times that are less than 300 microseconds. So here we see the units of microseconds. The bulk of the logs take between 100 and 170 microseconds, but there's a really long tail, and the histogram on the right is on log scale, so you can kind of see the tail a little bit more. So two things. It's a fairly long tail, even on a relatively sunny day environment, and we go all the way out to 3,300 microseconds, 3.3 milliseconds for a single log write. Right? What happened there? I don't know. We were on a VM as well, so there's other things that can contribute to this. The other thing is that if we had something like the write, with real-time latency and data, then as load builds up, you would see kind of jumps on the tail, right? Or maybe if in a prolonged busyness, the whole thing would shift to the right. So that's the value of having the distributions. The second example is the same idea, but I'm writing to an HTTP log forwarder. So instead of writing to a file system, I just wrote periodically logged to this and then measured the time. And here, the units are in milliseconds now because we're talking to a process and getting some act back. And so now the bulk is probably somewhere under 7 milliseconds. Again, a long tail with the max that I saw almost a quarter of a second. So pretty long tail. And the final example is synchronous writes. And I do want to take this kind of to try to dispel a common misconception, right? File system writes on Unix and Linux systems are kind of naturally asynchronous, meaning that when the write system call returns, the data is in the buffer or page cache, and some kernel thread is going to flush it out to disk later. Right? And so normal logging, which uses normal file system writes, are also asynchronous with respect to disk write, the disk writes. So and I think there's some confusion there because some people use async logging to try to avoid the disk bottleneck. It's the async logging in async loggers is trying to be asynchronous with respect to the write system call at least, or maybe even earlier. Right? So here I'm just doing sync writes, and so things like if you were using a database, to log to a database where you had auto commit. Right? That would involve a synchronous write on the database parts. You have to at least have one synchronous write. So again, this is not to drive your decision. It's to kind of motivate you to go back and do your own measurements. Okay, so now that we have this, right, now we can look at logs in a maybe a slightly wiser way, right? So if you have the pseudocode on the left and the log on the right, what I naturally do is say, oh, okay, this do talk operation took 2 milliseconds. The real thing to say is that log plus do talk took 2 milliseconds. So now you have to be kind of a little bit, given some data, right? Like the HTTP log is in the millisecond range. Then you have to kind of factor that into your interpretation of this data. And your log scrapers who are scraping these logs for metrics might have to do that as well, right? Okay. And again, this is where I kind of back up and stop picking on logging, right? That this lack of visibility into operations is a problem that we have for a lot of low-level services. And another example I want to give you amounts to my malloc moment, okay? And my malloc moment actually deserves a talk of its own, but I'm going to try to distill it like really fast. This was 2007, same messaging group that I was in, but we're running a guaranteed messaging broker in-house. What we would do is we would restart the servers every weekend. And someone noticed that after the restarts, the server was pretty zippy. But as the week went on, the server got more and more tired. It was kind of slowed. So once that was pointed out, we kind of looked at the system and said, oh, okay, the system CPU is also going up as the week went on too. Okay. So we did some profiling, and is the mic okay? Okay. So we did some profiling, and we found that the problem was malloc. Malloc was taking longer and longer as the week went on. Okay. And so after a lot of instrumentation and some code inspection, so this was glibc malloc, and so we basically had to instrument it and do some code inspection. We found out that servers naturally kind of do things over and over and over again, right? So this particular server was making allocation requests for an object of certain size. It was doing it over and over and over again. In this case, the way the malloc works is that it's kind of bins, and you try to look for a bin that satisfies your request. If you can't, it goes to the next bin until it finds one, and then breaks it up and puts it into the right free list, the remainder into the right free list. So the way this worked was that the size that it was asking for was causing its natural bin size to grow with never satisfying the request. So every request for that size made the search worse, right? One more. And so by the end of the week, you had like 1 million items on that free list to which malloc had to search to find that it couldn't satisfy and go to the next bin. So, and my point here is that my point is that this lack of visibility into malloc, right? If it could happen to the server, right? So it's dumb luck that the server chose this size that has a problem, right? But it's also dumb luck that you don't choose that size that has a problem. How do you know whether you're in that situation or not? Right? So without visibility into what malloc is doing, you don't. And so you may attribute the problem to something else if you're not kind of careful, right? Or you may just be relying on the weekend reboots, right? And you do a midweek reboot instead, right? But I think visibility into malloc here would have been very useful. Okay. And again, I'm not picking on malloc and logging. It really is. There's so many low-level services. If you go to performance-oriented talks at SREcon or any other conference, the first half of many of these kind of studies and talks involve kind of doing the clever instrumentation to kind of figure out where the problem is, and then doing some more instrumentation to kind of figure out what's going on inside, and then mitigating, right? If there was built-in visibility, then the first couple would probably not be as necessary. You'd be focusing on mitigation once you know. And actually, once that's known, then there's a feedback loop to developers to do something a little bit different, right? It's really a lot of blind spots here. Okay, so. Why are we in this state? I have some ideas, and I'd like to kind of go through them. The first is that I think that there's some confusion between metrics and logging. Right? So I had a role in capacity management after the financial crisis. I had to go to teams and look at how how they did their metric visibility for runtime. And I would say, okay, well, you need some metrics here and here and here. And what developers often did was whenever I said metrics, they wrote a log. So if you think that a metrics means a log, then you would never think to add metrics to a logger, because that would mean I'm going to log every time I log, right? So if you have the wrong idea of what metrics are, then you're not going to ask even the right questions. And you wouldn't ask for it either. So in reality, there's a visibility spectrum with logging on one end, which is fairly expensive, and metrics on the other end, which is intentionally inexpensive, right? So with logging, you're collecting a lot of context, you're collecting a lot of information, and you're keeping each event and kind of persisting that. With metrics, you're choosing to lose information about individual events, lose context information, and you're choosing to kind of keep a little kernel of information about what happened for compactness. And so in metrics, on the metrics end, we're trying to keep some information without incurring a lot of overhead. And that's what kernels have done for a long time, right? That they keep their metrics counters and accumulators in kernel address space, and they have some other mechanism for kind of accessing them, right? They have KMEM historically, or modern ones of /proc/system and such. But the key is that in order to kind of maintain metrics cheaply, you do this kind of condensation, right? And Java provides a similar model for JVMs with JMX, right? At JMX you have mbeans, and then you have mbean getters. And with metrics, I also want to point out that there's almost a free lunch with respect to metrics, in that if your metrics are kept in shared memory, then observers don't have to disturb the application to get at them, right? So there's no interaction with the application, and so that represents almost a free lunch. I'll go into that a little bit more in the next slide, hopefully. The second reason I think that we're in this situation is that we don't have a good standard for process application metrics. And this is the slide where I kind of look back at the last 30 years with regret and recrimination, because over 30 years ago, there was this group called the Performance Management Working Group, PMWG. And it was formed specifically by a consortium of Unix-interested tech companies to make sure that Unix got all the things that it needed to properly do performance management. I was a Bell Labs representative to that group, so companies like IBM and Amdahl, I think, were founding members of the group, and they want to kind of bring Unix up to like mainframe standards for performance management, which mainframes are pretty good at. The participants in the PMWG, we all had different perspectives and priorities, and for me, my thing was to kind of get at a very low cost, easy to use, low-level interface to get at data and to make data available. And I prototyped something that essentially made SAR data, if you're familiar with that, available read-only to all processes via memory dereference. So no system calls, no nothing, just to kind of dereference memory to get at SAR metrics. And on that, I was able to run SADC, the data collector component of SAR, 100 times a second with no measurable CPU overhead, right? Where at the time, this is a 3B2-400, if you know what that is. If you ran SADC once a second, that would incur 3 to 5% CPU. So I had like a very cheap interface, and the next thing would have been to add some discovery so you could find that memory address and port it to processes as well. But I didn't get to finish that work, and I left Bell Labs, and history shows that the performance management working group, for one reason or another, didn't kind of succeed in its goal. But our goal was to kind of get these interfaces. So again, why do we need this? So if you're a malloc maintainer, right, you're not going to add a dependency on some third-party metrics library in order to provide metrics for malloc, right? You want something low-level that you can depend on and not introduce a new dependency. So again, JMX provides a pretty good model, right? In JVMs, the JVM, the database drivers, the app servers, and the app all can expose metrics through the same mechanism. You can discover them, and you can access them through the same mechanism. And /proc kind of comes pretty close to this, right? /proc per PID, you can get at kernel level metrics. They're a fixed set of kernel metrics. So imagine a kind of mirror universe, where I have facial hair, and where /proc can be used to kind of by writers of malloc and loggers and other low-level code to export metrics that they're maintaining in in process address space. That's kind of the interface I believe that we're missing today. Okay, so finally, I think that we're ceding responsibility. We're in the state of learned helplessness. We've gotten used to the fact that we have no metrics, so we have no visibility into these layers, and we kind of accept it. We say, okay, even though malloc was implicated in my outage, and in the post-mortem, we said clearly the problem was malloc, right? We don't say, in app code, we say, okay, now we have to put some visibility around that so we know what's going on and going forward. In malloc, we say, okay, they get a free pass because they're malloc, right? Who's going to touch them, right? So we really should be kind of thinking about these low-level services that get implicated in antics and drift, and strive to kind of get visibility out of it. We have more power than we acknowledge, right? Because so this goes back to the fire escape talk last year. The idea that you kind of don't want to, it's not ideal to be kind of bolting fire escapes onto buildings that hadn't intended, or to put kind of sprinklers through buildings that weren't built for them. And you want to kind of build from scratch, right? That's the kind of idea about behind fire codes. But our modern systems aren't like monolithic buildings, right? They're kind of very dynamic, and they're more like Lego blocks that you assembled at runtime to get what you want. And so with that kind of late binding, there's a lot of opportunity for kind of behavior change, right, in the area of monitoring and such. So on my part, pretty much everywhere I've gone since I left Bell Labs, I've implemented a crude user-level equivalent analog to /proc, where the clients could register metrics, get memory out of areas backed by memory back file, and maintain the metrics. And so observers can kind of go and observe cheaply. I've taken opportunities like using LD preload and interposing to inject behavior. Like in the malloc case, that's what I did. And so we should not, if the vendor isn't providing, if the lower level isn't providing, we should kind of be looking at the tricks for kind of getting at it ourselves. If you look at the malloc, I think there's a malloc internals page. They actually recommend wrapping malloc to kind of get information. So some people recognize that problem. Okay, so I want to close by looping back to logging. And so I've talked about the latency and logging, and it's easy to kind of think that I'm saying don't log. That's not my message. My message is that log smarter, right? Have some idea of what the costs are so you can make some decisions. Loggers give you logging level decisions, right? Typically, those decisions have been made based on this space. But there's another dimension, which is latency, right, that it can be made on. Looking back in the last 10, 15 years, logs have evolved from being mainly used by human beings to being now, I think, primarily consumed by programs, log scrapers, log indexers. Right? So why are we still incurring the cost of kind of converting a timestamp into a human-readable form if that's the case? Right? I did some recent testing. So string F time on a Linux box and a Spark Solaris box that I had access to took about 15 microseconds. So it's now down to 15 microseconds instead of the 1 milliseconds from 10 years ago. But a stat system call is about 2 microseconds. So it's still multiples of a system call, right? So it's not cheap. And another side effect of having epoch-based timestamps would be to eliminate this kind of nasty time zone conversion that's so bad with distributed systems, right? If you don't have a time zone, then you have to kind of guess at what time the log was. So there's a lot of there are some benefits to kind of looking at our encoding and things, and maybe knowing how long these things take will drive those decisions. I've always had a kind of I don't know, uneasy feeling about async loggers. I don't believe that they do everything they say they do, and you give up a lot to use them. So with kind of visibility, you would kind of be able to better judge, because you trade off a lot. Async loggers on the burst buffer, and so you're not getting your logs, and if you crash, you lost useful information, right? So knowing whether async loggers are good for us or bad for us, or when is good, and more importantly, better runtime monitoring so that we can see the drifts and the antics, right, as they're occurring in production. So that's what I have. Thank you.
Thank you, Danny. We actually have time for maybe a couple of questions. If you have a question, please use the mic in the center aisle.
You seem to be a pretty big expert in your field. I really appreciated your talk. What would you say is the #1 thing that a lowly SRE could do to improve the performance of his logging pipeline?
Well, so I would say that the #1 thing that we could do is the first step wouldn't be improving. The first step is getting that visibility, right? So go back and do those tests on sunny day, right? Or do the test on a less than sunny day, right? Environment, and just to see. So that way you're a little bit more informed about when you read those logs and you infer those lapse times and such, that you have some information there. But I think that as a community, as users of the services and the data, we should be asking, like every time I ask, do you measure latency? No, right? I think that we should all be asking, do you please measure latency? Please provide metrics on this.
Time for one more question.
So when you mentioned synchronous logger and asynchronous logger, right? And you also mentioned that whenever we write, when we use a write system call, it actually gets buffered anyway, right? So in theory, it's asynchronous logging anyway, right? Because we are writing to some memory buffer, and then it will be dumped to the actual disk later on by the kernel. So in that way, do we really need to do asynchronous? Do we need to create a thread and do the logging, or it's just to use this thing?
Yeah, so when I made that statement, I made a simplification, right? Because to get that data into a system buffer, at times you may need to do a flush out, because all buffers may be dirty, so there may not be an available one. So you'll incur a delay there. But those things can be, I had an item up on file system strategies, right? So file system strategies can take care of that to make sure that that's available. So I oversimplified things a little, but yeah. And I'll be at the Bloomberg booth, so if you want to kind of talk some more, come by. Thank you.
Thanks again, Danny.